There is something in the room with you right now that, going by our best physics, just shouldn't be here. It's you. The stuff your hands are made of. The stuff in your bones, in your blood. All of it goes back to the very first second the universe existed. And in that first second, the rules we've worked out say it all should have been wiped out. Back then, the universe made two kinds of stuff in equal amounts, matter and its mirror twin. When the two touch, they don't bump and bounce off each other. They erase each other, and all that's left is a little flash of light. No stars, no planets. Nobody here to wonder about any of it. And yet here you are, made of the stuff that was never supposed to last. One extra piece out of every billion. That's the whole reason you exist. Where did that one piece come from? Take any particle of matter, an electron, say. Somewhere in the laws of physics there is permission for its exact opposite to exist. Same mass, opposite charge, a mirror version that is identical in every way except for the sign on a few of its properties. Bring the two together and there is no wreckage, no fragments, no smaller pieces. The mass of both converts entirely into energy and leaves as light. Two things become a flash of nothing. This was not discovered by smashing anything. It was discovered in an equation, in the 1920s, by a physicist named Paul Dirac, who was trying to describe how an electron moves when you take both Einstein's relativity and quantum mechanics seriously at the same time. The equation he wrote down worked. It described the electron beautifully, but it had a second solution he hadn't asked for and couldn't easily throw away. The math allowed an electron with a positive charge instead of a negative one, a particle that would attract another electron rather than repel it. Dirac knew of no such thing. Nothing in any laboratory had ever shown it. He could have dismissed the extra solution as a meaningless quirk of the algebra, the way you sometimes discard the negative root of a square. Instead, he took the mathematics at its word and suggested the particle might actually exist. It inverts the usual order of how we expect discovery to work. We tend to imagine science as looking at the world and then writing equations to describe it. Here it ran the other way. The equation came first, insisted on a particle nobody had seen, and a few years later, that exact particle turned up in cosmic rays raining down through the atmosphere from space, positively charged, the electron's mirror, precisely as the math had demanded. The universe contained something because an equation said it had to. The mirror was real, and we knew it was real before we ever found it. And it wasn't just the electron. Every particle that exists has a counterpart. The proton, that heavy lump sitting in the heart of every atom, has an oppositely charged twin. So does the neutron. There is, in principle, a complete shadow chemistry, an anti-periodic table, an anti-hydrogen, anti-stars, anti-worlds. Here is the part that unsettles people, and it should. There is nothing in the laws of physics that prefers matter to antimatter. The rules are very nearly symmetric. If you built a universe entirely out of antimatter, anti-chemistry would proceed exactly as ordinary chemistry does. Anti-stars would shine. An anti-you could be reading this and notice nothing strange at all. And antimatter isn't some rare laboratory curiosity that only exists where physicists conjure it. Your own body is making it right now. Among the atoms inside you is a small amount of a radioactive form of potassium, and as those atoms decay, a fraction of them throw off positrons, anti-electrons, at a rate of hundreds every hour. You are, very gently, an antimatter source. Each of those positrons survives only a flicker, because it immediately runs into one of the countless ordinary electrons packed into your tissue, and the two annihilate in a tiny burst of light deep inside you, unnoticed. The reason antimatter seems exotic isn't that it's hard to make. It's that the moment it appears, it's surrounded by an overwhelming ocean of ordinary matter waiting to cancel it. It vanishes because it's outnumbered, which is just the early universe imbalance, replayed in miniature, inside your body, every hour of your life. How do we even know we're the matter? How do we know we're not the antimatter? And it was ordinary matter that lost the fight at the beginning, and we just call our side matter because it's the side that's here. The honest answer is that the names are a convention. Matter is just the label we gave to the kind that survived. There's no deeper sense in which our side is the real one. But the convention doesn't change the mystery, because the mystery isn't about which side won. It's about the fact that one side won at all. A perfectly balanced start has no winner. It has two sides that erase each other completely. For our side, whichever side it is, to be standing here, something had to break the symmetry. Something had to tip the scale by the tiniest possible margin and let one type outlast the other. And we know exactly how tiny that margin was. This is the detail that turns the mystery from philosophy into measurement. When matter and antimatter annihilate, they leave light behind, and that light is still here. The afterglow of the early universe fills all of space, a faint sea of radiation we can measure in every direction, cooled now to barely a few degrees above absolute zero. Count the photons in that sea, and you are counting the ghosts of every annihilation that ever happened. Compare that number to the amount of matter left over in stars and gas and galaxies, and you can read the original ratio directly off the sky. For every billion particles of antimatter in the young universe, there were 1,000,001 particles of matter. Everything annihilated in matched pairs, 1,000,000,000 against 1,000,000,000, light flooding out, and one particle in every billion was left standing with no partner to cancel it. That leftover 1 in 1,000,000,000 is everything. It is every galaxy, every star, every planet, the entire visible universe, you included. We are the rounding error. We are what was left when almost everything canceled out. Put that ratio at human scale. Imagine a stadium crowd of 1,000,000,000 people on one side and 1,000,000,001 on the other, and at some signal each person finds their exact opposite in the other crowd, and the two of them vanish together in a burst of light. 1,000,000,000 pairs disappear. The stadium empties. And when the light fades, one single person is still standing in all that emptiness, and that one person has to become every living thing that follows. That is the proportion we are talking about. That is how close the universe came to being nothing. Now, you could reasonably object, maybe the imbalance isn't real everywhere. Maybe somewhere far out past what we can see, there's a region that went the other way, vast territories of antimatter, anti-galaxies, balancing the books on a scale too large for us to survey. It's a fair thought, and physicists took it seriously. The trouble is that if a region of matter ever touched a region of antimatter, the boundary between them would blaze with a very specific kind of radiation, the unmistakable gamma-ray signature of annihilation happening along a seam millions of light-years long. We've looked. The sky doesn't show those seams. As far as we can see, in every direction, it's matter all the way out. The imbalance isn't local. It looks like a property of the whole. So the books don't balance, and they don't balance everywhere at once, and the size of the imbalance is pinned down to 1 part in 1,000,000,000. That's not a vague mystery. That's a precise number, demanding a precise explanation. And the standard model of particle physics, our best, most tested theory of how particles behave, does contain a small built-in preference for matter. One of the 4 fundamental forces, the weak force, the one responsible for certain kinds of radioactive decay, treats matter and antimatter slightly differently. For a while that looked like it might be the answer. It isn't. The bias in the weak force is real, but when you work out how much asymmetry it could have produced in the early universe, it falls short, not by a little, but by a wide margin. It can account for a sliver of the imbalance. The rest has no explanation inside our current theory. Einstein's relativity doesn't supply one either. The gap between what our physics can produce and what the universe actually did is one of the largest holes in all of science, and it sits right at the foundation, before the first atom, before the first star, before structure of any kind could begin. To explain why almost no antimatter survived, you have to study antimatter directly, make it, hold it, and measure it against ordinary matter closely enough to find the difference that the early universe used and we can't yet see. The problem is that the moment you make antimatter, the universe around it tries to destroy it. So how do you hold the one substance that annihilates the instant it touches anything you could hold it with? There is exactly one place on Earth set up to make antimatter to order, store it, and study it. It sits underneath the border between Switzerland and France, inside the largest particle physics laboratory in the world, in a building plainly named the Antimatter Factory. The way they make it begins with violence. A ring 27 kilometers around accelerates protons until they are moving a hair below the speed of light, and then slams them into a metal target. The collision is so energetic that some of that energy doesn't stay as energy. It freezes back into matter, and a tiny fraction of that freezes into antimatter. This is the reverse of annihilation. Annihilation turns mass into light. This turns concentrated energy back into mass, including the mirror kind. Out of an enormous burst of collision energy, a small harvest of antiprotons is collected and slowed down for study. And slowed down is the whole trick, because a freshly made antiproton is moving far too fast to do anything useful with. So before it reaches the experiments, it's fed through a series of rings that don't speed it up, but bleed its speed away, cycling it for a couple of minutes in a large ring, then 15 seconds in a smaller one, until it's calm enough to catch. A single shot might deliver around 10 million antiprotons. By the time the losses of catching them are paid, the experiments aim to hold on to something like 1,000. And even that isn't the goal. The goal, in the most precise of these experiments, is to study them one at a time, a single particle of antimatter, isolated, interrogated. If everything around the antimatter is made of ordinary matter, the walls, the air, the instruments, the floor, why doesn't it just annihilate the instant it's made? What is it sitting in? It's sitting in almost nothing, held by fields that never touch it. The container is called a trap, and it works with magnetic and electric fields rather than physical walls. Charged antiprotons can be suspended in those fields, made to hover and circle in empty space, never resting against a surface. And the space itself is pumped down to a vacuum more extreme than the gaps between the stars. Interstellar space, the great emptiness between solar systems, still has the occasional stray atom drifting through it. The inside of an antimatter trap is emptier than that, deliberately, because every stray atom is a potential assassin. The antimatter survives because it is held in a pocket of engineered nothingness, levitating in a magnetic grip, kept away from every particle that would end it. The fragility is hard to overstate. If the trap so much as warms up, gas frozen onto its inner walls can lift off, drift inward, and find the antiprotons, and that's the end of them. The magnets holding everything in place have to stay colder than a specific threshold, just a few degrees above absolute zero, or they stop working as superconductors and the grip fails. Keeping antimatter is less like storing a substance and more like sustaining a held breath that must not be let out. Once it's held, what can you actually learn from it? You measure the things that the standard model says must be identical between a particle and its mirror twin, and you measure them to a precision that sounds invented. In one of these experiments, physicists combine the charge and the mass of a trapped antiproton into a single number and compare it against the same number for an ordinary proton, looking for any difference at all. So far, the two match to within 16 parts per trillion. That is the most precise comparison of matter and antimatter ever made. 16 parts per trillion is a hard thing to feel, so here is its size. A trillion seconds is a little under 32,000 years. 16 parts in a trillion is like measuring a span of 32,000 years and being uncertain by about 8 minutes across the whole of it. The proton and the antiproton have been checked against each other that closely, and they have not yet disagreed. Every measurement says they are the same, which is exactly the problem. Because if they are perfectly the same, the early universe had no reason to keep one and discard the other. To make antimatter you can really test, though an antiproton on its own isn't enough. You want a whole atom, the mirror of the simplest atom there is. Ordinary hydrogen is a single proton with a single electron bound to it. Antihydrogen is a single antiproton with an anti-electron, a positron, bound to it. Building one means producing antiprotons and positrons separately, cooling both, and coaxing them to come together and bind without either one touching the ordinary world on the way. It is far harder than holding a bare antiproton, and the progress on it tells you how brutal the work is. When physicists first managed to trap antihydrogen, they could hold on to roughly 1 atom for every 9 attempts. Now, on a good morning, the same effort yields tens of thousands of trapped atoms accumulated overnight. The leap from 1 in 9 to 20,000 is the difference between catching a single snowflake on your tongue and filling a jar with them, and it took years of patient engineering to cross. One of them is, essentially, what color is it? Every kind of atom absorbs and emits a very specific set of colors of light, a fingerprint as distinctive as a barcode, set by the exact arrangement of its inner workings. Ordinary hydrogen has its fingerprint, measured to extraordinary precision over a century. The question is whether antihydrogen has exactly the same one. If the mirror atom absorbs and emits light at precisely the same colors as ordinary hydrogen, that's one more way the two are identical. If even one color is off by a hair, that would be a crack, the first sign of a real difference. So far, the colors match. Another question is even more basic. Which way does antimatter fall? General relativity says it should fall down, the same as anything else. Gravity shouldn't care whether matter is ordinary or mirror. But should isn't measured. And for a long time, nobody had actually watched a piece of antimatter drop to see. A few years ago, physicists finally did it, released real atoms of antihydrogen, and watched which way they went. They fell down, the way ordinary atoms do. Another expected result, another door quietly closed on the more exotic ideas. It would have been a revolution if antimatter had fallen up. It didn't. The mirror keeps coming back ordinary in every way we test, which is exactly what makes its near-total absence from the universe so maddening. All of this is happening across not one experiment but a whole cluster of them under the same roof, several separate setups, each interrogating a different property of antimatter, each chasing the same buried question from a different angle. How much does it weigh? To the last decimal. What colors does it like? How does it respond to gravity? Is the antiproton, measured against the proton, identical down to the smallest fraction anyone can reach? The factory is less a single machine than a workshop full of people, each trying a different way to make the mirror confess a difference, and so far the mirror has stayed silent in every language they've tried. And the cost behind all of this is staggering, not because anyone is wasteful, but because the universe charges an enormous price for the smallest amount of this stuff. The total quantity of antimatter ever produced at the factory, gathered across its entire history, is measured in nanograms, billionths of a gram. If you annihilated all of it at once, you'd get roughly enough energy to run a single household light bulb for a few hours, worked out per gram. That puts the price of antimatter somewhere above $60 trillion a gram. And at current production rates, making a single gram would take on the order of 1 billion years. It is, by a wide margin, the most expensive material on the planet, and we make it not to use it, but to ask it a single question. Are you truly identical to your mirror image? Because if you are, we shouldn't be here to ask. Every time an experiment fails to find a difference between matter and antimatter, it isn't a wasted result. It's a wall going up. Each non-difference, measured more finely than the last, rules out a whole class of explanations for how the universe started, the more exotic theories that predicted a difference big enough to have already shown up by now. The silence is informative. We are narrowing the hiding place of the answer by confirming over and over the places it is not. The antimatter factory is a violent place to do delicate work. The same facility that can manufacture antimatter is full of powerful magnets, electrical equipment, and radio frequency noise, fluctuating fields and electronic chatter from every machine running nearby. When you're trying to measure an antiproton to 16 parts in a trillion, that environment is like trying to hear a pin drop inside a running factory. The better the measurements need to get, the more that background noise becomes the wall you can't push past. The experiment has become, in a sense, a victim of its own success, precise enough that its own surroundings are now the limiting factor. So physicists hit on an audacious fix: take the antimatter out of the factory, build a trap that can hold antiprotons while it travels, load it onto a vehicle, and drive the antimatter away to a quieter laboratory with far less magnetic and electrical interference, where the measurements can be pushed to limits the noisy factory could never reach. It sounds absurd the first time you hear it, and people's first reaction tends to be a joke about a special antimatter truck barreling down the highway. The reality is almost as strange as the joke. The portable trap is a roughly 1-ton contraption holding a liquid helium tank to keep its magnet cold, a battery system to keep the trap powered and the antiprotons levitating through the whole journey, and monitors watching the temperature and helium level so nothing drifts out of the narrow band where the antimatter stays alive, and the truck carrying it is, by design, an ordinary truck, nothing exotic. A regular vehicle, with about a ton of cutting-edge physics riding in the back, and inside that, a pocket of vacuum emptier than interstellar space holding a handful of the most expensive particles on Earth. It has actually been done. Antimatter particles caught, sealed in the portable trap, and successfully moved across the laboratory campus, the first short trip of a plan that aims eventually to ferry antimatter to specialized labs scattered across a continent. Picture that as a near-future fact. Somewhere on an ordinary road, mixed in with the lorries carrying groceries and furniture, a truck quietly carrying a sample of antimatter to a lab where it can be measured in peace. The point of all that effort is to escape the noise and compare matter and antimatter even more precisely than the factory allows. And, if no difference ever shows up even at those extreme limits, to keep ruling out the more exotic stories about how the universe began, narrowing the answer by elimination. But narrowing isn't finding. After all the traps and all the precision, the central difference, the thing that let matter win, has still not appeared in any of these measurements. So if it isn't hiding in the mass or the charge of the antiproton, the search has to widen. It has to move to stranger particles and to a process so rare it may happen once in a span of time longer than the universe has existed. Where do you even look for a difference that has refused to show itself in the most precise instruments ever built? The places we've looked so far all share an assumption that a particle and its antiparticle are two distinct things. An antiproton is clearly not a proton. It carries the opposite charge, and you could in principle tell them apart by watching how they bend in a magnetic field. The same goes for the electron and the positron. Opposite charges, different objects, mirror images that are truly separate. But there is one particle in nature that breaks this neatly into doubt, and it may be the key to the whole asymmetry. It's called the neutrino, a particle so faint and so reluctant to interact that trillions of them are streaming through your body every second, pouring out of the sun and through the entire Earth as if it were empty glass, and not one in a lifetime is likely to touch a single atom of you. They are produced in vast numbers in nuclear reactions, including the radioactive decays that the weak force governs. And the neutrino has a strange property that charged particles don't. It has no electric charge. That matters more than it sounds. The thing that lets you distinguish an antiproton from a proton is the charge, the opposite sign. But a neutrino has no charge to flip. So there is a real, open question, one of the deepest in physics. Is the antineutrino actually a different particle from the neutrino, or are they the same thing seen from two sides? A particle that is its own antiparticle, a mirror image that is the original. If that's true, and right now we don't know, it would change everything about the matter question. Because a particle that is its own antiparticle can do something forbidden to particles that aren't. It can quietly tip the balance between matter and antimatter through a chain of decays that has no counterpart in the ordinary rules. This is what an experiment buried deep under a mountain in Italy is built to catch, shielded from the constant rain of cosmic particles by 1.5 kilometers of solid rock overhead. It hunts for an event so rare it has never been confirmed to happen even once. Start with an ordinary kind of radioactive decay to see what it's looking for. Inside certain atoms, a neutron can turn into a proton, spitting out an electron, and, our theories say, an antineutrino to go with it. That's the normal process, seen countless times. Some atoms can't decay that way, one neutron at a time, so they do it in pairs. 2 neutrons turn into 2 protons at once, throwing out 2 electrons and 2 antineutrinos. That's rare, but real, and it's been observed. Now here is the door that opens if the neutrino is its own mirror. If the antineutrino from one of those decays is identical to a neutrino, then instead of escaping, it could be absorbed by the other decay happening right beside it. The 2 antineutrinos, being their own opposites, could meet and cancel internally. The result would be 2 neutrons becoming 2 protons, 2 electrons flying out, and no neutrinos at all. The particles that were supposed to carry away the balance simply never leave. Finding a single one of those events, a decay where the neutrinos cancel instead of escaping, would be the first direct evidence of a particle behaving as its own antiparticle. And that behavior, scaled up to the conditions of the early universe, could be the seed of the whole imbalance. It would be the first real crumb on a trail leading back to why there is something here instead of a cooling fog of light. Not the full answer. The first crumb. It hasn't been found. After decades of building colder traps, deeper detectors, more shielded mountains, and more precise instruments than have ever existed, the difference that built the universe has not appeared. We can make antimatter. We can hold it. We can measure it against ordinary matter to a precision that borders on the absurd. And every time, it comes back identical, and the universe keeps refusing to explain how it chose. We understand an enormous amount, precisely enough to put a number like 1 in a billion on the imbalance and to measure a proton against an antiproton to 16 parts in a trillion. But there's a version of it that is exactly right, and it's this. The better our instruments get, the more sharply they outline the shape of what we can't yet explain. We are not confused in the way someone is confused who knows nothing. We are confused in the much more specific way of someone who has measured a thing precisely and found that it disagrees with everything they expected. That is a more honest place to stand, and it is the place the rest of this story lives in. Because the asymmetry isn't even the last strange thing. It's the first. It's the reason there's any matter at all. And the moment you have matter that survived, you run straight into the next problem, which is what that surviving matter did next. It didn't spread out evenly. It didn't stay a smooth fog. It gathered, it clumped, it organized itself across billions of years into the largest structures that exist, and the shape it chose is one almost nobody expects the first time they see it. If the universe began smooth, what told the matter where to go? There are actually 2 opposite puzzles hiding inside that question, and they pull against each other. The first is that the early universe was astonishingly smooth, far smoother than it had any right to be. The second is that it wasn't perfectly smooth, and the tiny deviations from smoothness are the seeds of everything. Both facts are strange, and the attempt to explain them at once led to one of the boldest ideas in cosmology. Start with the smoothness. When we look at the oldest light coming from opposite sides of the sky, the temperature is the same to better than 1 part in 100,000. That sounds like a tidy fact until you work out what it implies. Those 2 patches of sky, on opposite sides of us, are so far apart that in the entire history of the universe, light has never had time to travel from one to the other. They have never been in contact. Nothing, No signal, no heat, no influence of any kind, since nothing outruns light, could ever have passed between them. And yet they sit at the same temperature to exquisite precision. That should be impossible. If you walk into a house and every room is exactly the same temperature, you assume the air has had time to mix, or a furnace has reached them all. You'd be deeply confused to find two rooms at an identical temperature if you knew for a fact that no air, no heat, nothing whatsoever had ever passed between them, and that they'd been sealed apart since the house was built. That's the situation across the sky. Regions that could never have exchanged anything, that have no shared history at all, somehow came out matched. Either it's an absurd coincidence repeated in every direction, or something happened in the first instance that we're missing. The idea is that in the very first sliver of a second, far less than a blink, the universe underwent a burst of expansion so violent and so fast that it ballooned from smaller than an atom to enormous size almost instantly, stretching by a factor so large the number is hard to even write down. The proposal is that before that burst, the regions that are now on opposite sides of the sky were packed close together, in contact, sharing heat and settling to the same temperature, and then the sudden expansion flung them impossibly far apart, carrying their matched temperatures with them. The uniformity isn't a coincidence. It's a memory of a time when everything now distant was once neighbors, before a moment of runaway growth tore them apart. If that early burst of expansion really happened, then the unavoidable tiny jitters of the quantum world, the small restless fluctuations that exist even in empty space at the smallest scales, would have been caught up in it and stretched along with everything else. Fluctuations that began microscopic would have been blown up to enormous size, frozen into the fabric of the universe as faint regions of slightly more and slightly less density. The same stretching that smoothed the universe overall would have printed onto it a pattern of tiny irregularities, the exact seeds that gravity would later grow into filaments and galaxies. The structure of everything large would, in this framework, be the fossil of something unimaginably small, magnified across the whole sky. It's a beautiful idea, and it's important to be honest that it's not settled fact. It explains the smoothness. It explains the seeds. It makes predictions that match the pattern in the oldest light well, but the underlying cause of that early burst, what drove it, and exactly how it ended, remains entirely unknown. We have a framework that works remarkably well, and a mechanism underneath it that we can't fully describe. That's a recurring shape in this story, a model that fits the data sitting on top of a foundation we can't yet see clearly. But take the framework at its word for a moment, and something quietly staggering follows. The largest structures in existence, the web of galaxies spanning the observable universe, would be the direct descendants of the smallest flickers there are, the quantum restlessness of almost empty space, stretched to cosmic size, and then patiently amplified by gravity over billions of years. The biggest things would be the oldest, faintest, small things, grown up. So the ripples had a source, and the smoothness had a cause, and both trace back to that first violent instant. Now the question is, what gravity did with those ripples over the billions of years that followed? Look at a map of the universe on the largest scales. Not one galaxy, not 1,000, but millions of them plotted by position. And the thing that jumps out is that the galaxies are not scattered like sand. They're strung. They lie along threads. The threads cross at dense knots crowded with galaxies, and they stretch away into long, thin filaments. And between the filaments are enormous rounded voids where there is almost nothing at all. The whole arrangement looks unnervingly organic, like a cross-section of bone, or a neural network, or the branching of something grown rather than scattered. Astronomers call it the cosmic web, and it is the actual large-scale shape of the universe. The first instinct is to ask what built it. What force reached across those distances and arranged galaxies into threads? But the threads came first. The galaxies formed along a scaffolding that was already there, laid down when the universe was a fraction of its current age, long before a single star had lit. You can see the blueprint directly. in that same afterglow of the early universe we used to count the annihilation photons. When you image that radiation across the whole sky in fine enough detail, it isn't perfectly uniform. There are faint patches, slightly warmer and slightly cooler, differences of less than 1 part in 100,000. Those patches are the imprint of tiny variations in density in the infant universe, places where matter was packed a hair more tightly than average, and places where it was a hair thinner. A difference of 1 part in 100,000 is almost nothing. It's the difference between a still pond and a pond with ripples too small to see, but it was enough. It was enough because gravity is patient and it never stops. A region with slightly more matter pulls slightly harder. Pulling harder, it gathers more. Gathering more, it pulls harder still. Over hundreds of millions of years, those faint, overdense patches drew matter out of the thinner regions around them, deepening the contrast until the slightly denser places had become threads packed with gas and galaxies, and the slightly thinner places had been swept into vast, empty voids. The structure didn't need a sculptor. It only needed a tiny head start and an enormous amount of time. The ripple in the early light became the skeleton of everything. Our own address sits inside this structure, and tracing it outward is a quick way to feel how large the scaffolding runs. Our galaxy belongs to a small cluster of a few dozen galaxies. That small cluster is one outlying member of a much larger collection, a supercluster threaded along the web, containing on the order of 100,000 galaxies and measuring something like 500 million light-years across. And every one of those galaxies is strung along the filaments like water beads clinging to a spider's thread after rain, perched at the edges of the great voids. We are not at the center of anything. We are a single drop on one strand of a web whose full extent we are still mapping. And the threads, dramatic as they are not the largest feature of the web. The voids are. Between the filaments lie rounded emptinesses that can span hundreds of millions of light-years, regions so devoid of galaxies that if you were inside one, the nearest other galaxies might be too far to see at all. These voids take up most of the volume of the universe. The bright structure, the galaxies, the clusters, the glowing threads, is a thin tracery wrapped around enormous bubbles of near nothing. It's tempting to think of galaxies as the main content of the cosmos and the gaps as the background, but by sheer volume it's the reverse. The universe is mostly void, with matter pressed into the seams between the empty spaces, like foam where the thin films cling to the edges of the bubbles, and the bubbles themselves are vast and hollow. The structure we marvel at is the rind. The emptiness is the bulk. That alone quietly upends the first instinct anyone has about what the universe is mostly made of, before dark matter or dark energy even enter the picture. When astronomers chart the cosmic web, what they're really charting is the galaxies, the bright beads. The galaxies are where the gas has collapsed and lit up, so they're easy to spot, and plotting their positions traces the rough shape of the threads. What we mostly cannot see is the threads themselves, the diffuse material strung between the bright knots, the actual substance of the filaments. We've been mapping the web by its decorations, not its strands. And that gap connects directly back to a budget problem that had been quietly haunting cosmology for decades. We know, with real precision, how much ordinary matter the universe is supposed to contain. We can read it off the early universe radiation, the same way we read the annihilation ratio. The number is firm. The trouble is that when astronomers go out and add up all the ordinary matter they can actually find, every star, every cloud of gas, every wisp of glowing plasma in every galaxy, they come up far short. A large fraction of the ordinary matter that must exist, that the early universe demonstrably made, simply could not be found anywhere. Not the exotic dark matter, that's a separate mystery for later. This is ordinary matter, the same kind you're made of, the kind that should glow or absorb light or show itself somehow. We knew how much there should be. We counted what we could see, and a huge piece of it was missing. If the early universe made that matter, and the books say it has to be somewhere, then where did almost half of the ordinary universe go? Before chasing where the matter went, one question comes first. How can we claim to know how much there should be at all? We weren't there. No one counted the atoms when the universe was young. The confidence behind every missing matter, and the books don't balance, rests on a single astonishing source of information, a light that has been traveling toward us since long before there were stars and is still arriving from every direction at this moment. When the universe was very young, it was not the cold, transparent, mostly empty place it is now. It was hot, dense, and opaque, a glowing fog of particles packed so tightly that light couldn't travel in a straight line. A photon would move a tiny distance and immediately scatter off a free electron like a beam of light trying to cross a thick mist. In that era, you couldn't have seen across a room, because light couldn't cross a room without being knocked off course. The whole universe was a furnace with no clear view through it. Then it cooled, about 380,000 years after the beginning, which sounds like a long time but is the blink of an eye against the universe's full age. The temperature dropped far enough that the free electrons could finally settle down and bind to nuclei, forming the first complete neutral atoms. And the moment the electrons were captured into atoms, the fog lifted. With the free electrons gone, light suddenly had nothing to scatter off. It could stream freely across space for the first time. The universe became transparent in an instant, on cosmic terms, and the light that was set loose at that moment has been traveling ever since. That light is still here. It fills all of space, coming from every direction, and we detect it now not as the fierce glow it once was, but as a faint hiss of microwaves, stretched and cooled by billions of years of expansion until it sits just a few degrees above absolute zero. It is the single oldest thing anyone can observe, a direct image of the universe as it was at 380,000 years old, the surface of that last moment of fog before everything went clear. We are, in a real sense, looking at a baby photograph of the cosmos, taken before it had stars, and the photograph is wrapped around us in every direction at once. To picture how this lets us reconstruct the past, imagine arriving at the scene of an explosion long after it happened. Fragments are strewn everywhere, and from the wreckage alone you'd struggle to say what the original object was. But then someone hands you a sharp photograph taken in the first instant of the blast, and suddenly you can trace each fragment back to where it started, run the whole thing forward in your mind, and understand the explosion you never witnessed. The oldest light is that photograph. It captures the universe near its beginning, and from the details frozen into it we can run the cosmos forward and check whether our model reproduces the universe we actually live in. And the details in it are extraordinarily specific. When the image is mapped finely enough, it's not perfectly smooth. It carries faint patches slightly warmer and slightly cooler than average, those 1 part in 100,000 variations that became the seeds of the cosmic web. But the exact pattern of those patches, how big they tend to be, how they cluster, how strongly the temperature varies from place to place, encodes the actual recipe of the universe. The physics that produced that pattern depended on precisely how much ordinary matter was present, how much dark matter, how fast everything was expanding. So, by measuring the pattern, cosmologists can read those quantities straight off the sky to a precision of a few percent. That's where the budget comes from. That's how we can say, with real confidence, that ordinary matter is about 5% of everything, dark matter about a quarter, dark energy the rest, and how we can count the atoms that ought to exist today closely enough to notice when 40% of them have gone missing. The accusation of missing matter isn't a vague suspicion. It's the difference between an inventory taken from the oldest light, which we trust because the same image predicts so many other things correctly, and the much smaller inventory we can actually find with telescopes. The shortfall isn't a gap in a rough estimate. It's a disagreement between two careful measurements, one reading the universe's contents from its baby photo, the other adding up what we can see now. And for decades, those two numbers refused to match. The oldest light says the matter is there. Our telescopes couldn't find it. So either the oldest light is misleading us about how much ordinary matter exists, or the matter is real and hiding somewhere we hadn't yet learned to look. Start with the size of the gap, because it's larger than missing usually implies. When you tally everything ordinary that shines or absorbs, all the stars, all the gas inside galaxies, all the hot plasma we can detect, you find roughly 60% of the ordinary matter the universe is supposed to hold. The other 40% had no home. It wasn't a small discrepancy to be cleaned up later. 4 out of every 10 particles of ordinary matter in existence were unaccounted for decades. And that's a statement about the visible, touchable, you and me kind of matter. There's a temptation to fold this into the more famous mysteries. Dark matter, dark energy, but it's a different problem, and in a way, a more embarrassing one. With dark matter, we at least have an excuse. It doesn't interact with light, so of course it's hard to see. The missing ordinary matter has no such excuse. It's the normal stuff. It should be detectable. We just couldn't find where it was sitting. The leading suspicion pointed back to the threads of the cosmic web, the strands we couldn't see directly. The idea was that the missing ordinary matter wasn't bound up inside galaxies at all, but spread along the filaments between them, as gas so thin and so hot that it barely announced itself. Thin, because it's smeared across millions of light years. Hot, because falling into the gravitational scaffolding of the web heats gas to extreme temperatures. Gas like that doesn't glow in ordinary light in any clear way. It emits faintly, in X-rays, at a level almost lost against everything else in the sky. The matter wasn't gone. The hypothesis said it was hiding in plain sight, strung along the very threads we'd been failing to image, too diffuse and too faint to pick out. Walk the actual trail of attempts, because it shows how long the matter is in the filaments, stayed a believable hunch that the universe refused to confirm cleanly. About 2 decades ago, an X-ray observatory caught 2 large clouds of diffuse gas floating between distant galaxies, not around a single galaxy, where such clouds were already known, but out in the gulf between them. It looked like it could be gas strung on the cosmic web, possibly some of the missing matter. But the glow was too faint to isolate with confidence. A few years later, astronomers combined many images to infer a filament funneling matter into a galaxy cluster, but they found it indirectly by watching how the filament's gravity bent the light of galaxies behind it, not by seeing the gas itself. Then came a clever trick. Catch a filament in the act of being lit up. When a brilliant, distant beacon happens to shine through a thread of hydrogen gas, the gas fluoresces, glowing under the external light like fog caught in a headlight beam. Using that, astronomers directly imaged a filament of hydrogen gas stretching nearly 2 million light-years, and later, whole networks of such threads around a dense young cluster, the first times parts of the cosmic web were seen directly rather than inferred. But every one of those wins came with the same asterisk. The gas was only visible because something external was illuminating it, or because it was the cooler hydrogen of the distant, early universe rather than the hot, thin gas that our models say holds most of the missing matter in the nearby cosmos. To see a filament glowing on its own, in the local universe, holding the hot diffuse gas itself, you needed a different approach, and even when a dedicated instrument began mapping faint emission and building 3-dimensional charts of these threads, and even when, early last year, a team captured an unusually clear image of a filament around a pair of bright galaxies a few million light-years long, the catch held. Those traced cooler gas, billions of years in the past, not the hot local material where most of the missing matter is thought to hide. The faintest, hardest, most important version of the target stayed unconfirmed. A hypothesis like that is easy to state and brutal to prove. For years, the detections were tantalizing and never quite clean. Astronomers found suggestive clouds of gas between galaxies. They inferred the presence of filaments indirectly by watching how the gravity of an unseen thread bent the light of galaxies behind it. They caught filaments lit up by chance when a brilliant distant object happened to shine through one like a flashlight through fog. Each result nudged closer, and each came with a caveat: too faint to isolate, or only visible because something external was illuminating it, or detected only as a statistical hint rather than a clear picture. The thread itself, glowing on its own in the nearby universe, hot and diffuse and holding the missing matter, stayed just out of reach. Then, in June of last year, it was pinned down. A team mapped a single filament of the cosmic web in faint X-ray light and isolated the hot, thin gas inside it well enough to measure it directly. To do it, they used two X-ray telescopes in tandem, one to map the filament's dim glow across a wide stretch of sky, the other to find and subtract the bright contaminating sources sprinkled along the same line of sight, chiefly the glare of supermassive black holes that would otherwise drown the faint thread. Strip those out, and what remained was the filament itself, finally seen on its own terms. Take the numbers on that single thread one at a time. It stretches 23 million light-years between galaxy clusters. That distance is so far beyond ordinary comparison that the only honest way to scale it is against galaxies themselves. Laid end to end, it would take roughly 230 galaxies the size of our own Milky Way to span the length of this one filament. Its mass comes to about 10 times the entire Milky Way, 10 galaxies worth of material, strung out as gas so sparse you could stand in the middle of it and never know. And its temperature runs to around 10 million degrees, hot enough that the gas radiates in X-rays at all, which is the only reason it could be found. It sits inside one of the most crowded regions of the nearby universe, a supercluster of more than 8,000 galaxies, and it connects 4 of those galaxy clusters along a single bright vein. The filament looked the way large-scale simulations of the universe had long predicted such a thread should look. The right temperature, the right density, the right shape, holding the right kind of matter in the right place. After decades of the books not balancing, here was a piece of the missing ordinary matter, exactly where the models said to look, behaving exactly as the models said it should. And that is reassuring, for about as long as it takes to remember the scale of the claim, because this is one filament, one thread, in one supercluster, mapped in heroic detail. The cosmic web has uncounted filaments laced across the entire observable universe, and confirming that a single strand contains its share of the missing matter is not the same as confirming that the whole skeleton does. It's the difference between finding one bone exactly where the anatomy chart predicted and concluding you've verified the entire body. One match is encouraging. It is not proof that the structure as a whole is what we think it is. Our model of the universe is extraordinarily good at telling us what should be there. Time and again, it has done exactly that. Predicted a quantity of matter, predicted the shape of a filament, predicted where the missing pieces ought to hide. And time and again, finding those pieces has taken decades of effort and the most sensitive instruments ever built. And even then, we've confirmed only fragments of the whole. The model passes every test we can actually run. We just can't yet run enough of them to know whether it's right about the universe or only right about the corners we've checked. To know that, you'd need to map not one filament but the whole web, to trace the entire skeleton and see whether the predicted scaffolding really matches the universe's true architecture. Missions are being built to attempt exactly that, to chart the shapes and distances of vast numbers of galaxies and infer the hidden threads between them. Within a few years, that effort may either confirm that the cosmic web is laid out precisely as the standard model demands, which would be one of the strongest validations the model has ever received, or reveal that it isn't, that something in our picture of matter or gravity or the early universe is wrong at the largest scales. But there's a deeper crack that doesn't wait for that map, and it doesn't involve missing matter at all. It involves something we thought we already knew: cold, a single number. The most basic number in all of cosmology, the rate at which the universe is expanding. We have 2 excellent ways to measure it. They were supposed to agree. They don't. To feel why 2 disagreeing measurements of the expansion rate count as a crisis rather than a curiosity, It helps to know how hard-won the expansion was in the first place, how recently we learned the universe was even large enough to expand. For almost all of human history, the cosmos was small, and worse, it was centered on us. The oldest pictures put the Earth at the middle of everything, fixed and still, with the sun and moon and stars wheeling around it on turning spheres. That model wasn't stupid. It matched what anyone can see with their own eyes. Night after night, the sky does appear to turn around a motionless ground. It held for more than 1,000 years, and it took real courage to displace it. When it was finally proposed that the Earth is just one of several worlds circling the sun, the idea was radical enough to be dangerous, because it demoted us from the center to a passenger. Even then, the sun was assumed to sit at the heart of all things, with the stars a fixed backdrop not far beyond. The next demotion came when astronomers mapped the band of light across our night sky and worked out that it's a vast disk of stars seen edge-on, our galaxy, and that the sun is one ordinary star somewhere inside it, nowhere near the middle. But even that left a much larger question wide open, and it was still undecided barely a century ago. Was our galaxy the entire universe? Or were the faint smudges of light scattered among the stars, other galaxies, separate islands of stars, impossibly far away? Serious astronomers argued both sides. The whole question of how big reality is came down to what those smudges were. It was settled in the 1920s, and the key that opened it came from a particular kind of star, one that pulses, brightening and dimming on a regular cycle. Earlier, a careful study of thousands of these variable stars had revealed something remarkable. The rhythm of their pulsing is tied directly to their true brightness. A slow pulse means a truly bright star. A fast one means a fainter star. And once you know how bright a star truly is, comparing that to how bright it looks tells you how far away it must be. These pulsing stars became measuring rods for cosmic distance, the first reliable way to gauge the gulf to things far beyond our reach. Pointing the largest telescope of the day at one of those faint smudges, the one in the constellation Andromeda, an astronomer managed to pick out individual pulsing stars inside it, measured their rhythm, and worked out their distance. The number was staggering. The smudge wasn't a cloud of gas within our galaxy. It was hundreds of thousands of light-years away, far too distant to be part of the Milky Way at all. It was another galaxy, with its own hundreds of billions of stars. Overnight, the universe stopped being one galaxy and became a place with countless galaxies in it, scattered across distances that dwarfed everything we'd imagined. The same telescope went on to find and measure others, some millions of light-years off. The cosmos had just become almost unimaginably larger than the one humans had lived in the day before. And then came the observation that mattered most for tonight. Studying the light from those distant galaxies, astronomers noticed that the colors were shifted, stretched toward the red end of the spectrum, the signature of an object moving away. Nearly every galaxy showed it. Almost everything was receding from us. That alone was strange, but the decisive detail was subtler. The farther away a galaxy was, the more its light was stretched, and so the faster it was rushing away. Near galaxies drifted off slowly. Distant ones fled at tremendous speed, and the relationship between distance and speed was steady and direct. There's really only one way to read that. If everything is moving away, and the more distant things are moving away faster, in every direction at once, then the space between the galaxies is expanding uniformly everywhere. It's the behavior of dots drawn on a balloon as it inflates. Every dot moves away from every other dot, and from the viewpoint of any single dot, the far ones recede fastest, even though no dot is special, and none is at the center. We aren't at the middle of the fleeing. There is no middle. The whole fabric is stretching, and we happen to be riding one point of it. That single realization is the root of the entire framework we've been leaning on all night. The expanding universe, the idea of a hot, dense beginning that everything has been spreading out from ever since, the whole timeline of cosmic history, and the rate of that expansion, the number tying it all together, has been measured and remeasured ever since, refined for the better part of a century. It became one of the bedrock values of cosmology, the figure feeding into the age of the universe, its size, the timing of everything in it. Which is exactly why it's so destabilizing that, after all that refinement, the bedrock has split into two numbers that won't reconcile. The expansion of the universe is not a theory anymore. It's an observation, almost 100 years old. In the 1920s, it became clear that nearly every galaxy is moving away from us, and this was the decisive part. The farther away a galaxy is, the faster it's receding. That pattern only makes sense one way. The space between galaxies is stretching. Everything is drifting apart because the distances themselves are growing. The rate of that stretching has a name and a value, and it underpins the entire science. From it, we calculate the age of the universe, the size of the observable universe, the timeline of when galaxies formed, and how clusters grew. Get that number, and a great deal of cosmology falls into place. It is, by a wide margin, one of the most consequential single numbers in physics. There are two clean, independent ways to measure it, and the trouble is entirely in the fact that they're independent, that they come at the answer from opposite ends of cosmic history and ought to meet in the middle. The first way looks at the universe as it is now. You find objects whose true brightness you understand, certain kinds of stars that pulse at a rate tied to their luminosity, and certain kinds of stellar explosions that all detonate at nearly the same intrinsic brightness. Because you know how bright they really are, you can tell how far away they are from how dim they appear. Then you measure how much their light has been stretched by the expansion, which tells you how fast they're receding. Distance and speed together give you the expansion rate, measured directly in the nearby, present-day universe. Refined over many years, this method lands on a value of around 73. The second way starts at the opposite end of time. It takes the early universe radiation, that same ancient afterglow, which is effectively a photograph of the cosmos when it was a few 100,000 years old, and uses the detailed pattern of warm and cool patches in it, together with the physics of how the universe has evolved since, to compute what the present expansion rate must be. It's not a guess. It's a tightly constrained calculation rooted in the best measured image in cosmology, and it produces a value of around 67. 73 from the late universe. 67 from the early universe. Both are measuring the same thing, the rate the universe is expanding right now. They are not supposed to be two different numbers. They're supposed to be one number, approached two ways. Early in any hard measurement, the error bars are wide, and a disagreement can be nothing more than noise. Two estimates that look different only because neither is precise yet, destined to slide together as the data improves. For a while, that's what most people assumed was happening here. It would resolve. The numbers would converge. As the measurements on both sides have grown more precise, more stars, more explosions, more independent techniques on the near side, a sharper image and tighter analysis on the far side, the two values have not drifted toward each other. They've dug in. The error bars have shrunk around two separate numbers, which is the opposite of what a measurement problem looks like. A measurement problem gets smaller as you measure better. This has gotten more solid. The gap is now too large, and both sides too precise, for it to be comfortably blamed on anyone's mistake. Astronomers have used entirely different distance methods. Geometric measurements anchored on bright sources orbiting the centers of distant galaxies, fresh surveys of stellar explosions across galaxy clusters, new calibrations using other kinds of pulsing stars, and the near-universe answers keep coming back high, clustered around the low to mid-70s, and keep landing far outside the range the early universe method allows. It isn't one stubborn result against the tide. It's a whole family of present-day measurements agreeing with each other and disagreeing with the past. There's a method that uses certain galaxies which host intense natural beams of microwave radiation near their central black holes, a kind of cosmic equivalent of a laser, but in microwaves. Because those beams can be mapped with extreme precision, they give a very clean geometric distance to the galaxy, free of many of the assumptions other methods carry. That technique landed near 74. A separate study used a dozen stellar explosions scattered across a single galaxy cluster a few 100 million light-years away and came out even higher, in the mid-70s. Another, just recently, used a different family of pulsing variable stars as the distance anchors instead of the usual ones, a clean, independent cross-check, and landed near 73 again. Each of these uses different objects, different assumptions, different possible sources of error, and they keep agreeing with each other in the low to mid-70s and keep refusing to drop down to the 67 the early universe demands. When several independent roads all lead to the same wrong-looking place, it gets very hard to believe they all took the same wrong turn. Some of the researchers behind the most precise present-day values have said outright that the model of cosmology might be broken and that what used to be politely called attention is starting to feel like a crisis. That word choice matters coming from them because they are the ones who would most want the measurements to be wrong in some boring, fixable way, and instead, they're the ones raising the alarm. We have one universe. It has one rate of expansion right now, and our two best, most carefully calibrated ways of determining that single rate give two answers that exclude each other. This isn't a case of not knowing the number. It's a case of getting two different numbers, each measured well enough that it shouldn't be wrong, for a quantity that can only have one true value. If the theory doesn't match reality, then the theory is wrong. It's a clean instinct, and it's not entirely fair. But it's not entirely wrong either, and the honest answer is more uncomfortable than either dismissing it or accepting it. The model of cosmology we've been using, the one that predicted the cosmic filament so well, the one that's passed test after test, depends on the expansion rate being a single consistent value. When two trustworthy measurements of that value refuse to agree, you are looking at one of three possibilities. Either one of the measurements has a flaw so subtle that years of scrutiny haven't found it, or there is some unknown source of error shared across many independent methods which would itself be strange, or the model is missing something real, something about the early universe, or about the mysterious force driving the expansion, or even about gravity itself. And that missing piece is what's bending the two answers apart. And the stakes ride on which number is right in a way that reaches all the way to the end of time. If the lower, early universe value holds, we live in a universe a little under 14 billion years old, expanding in a steady, predictable way toward a calm and distant future. If the higher, present-day value is the true one, then the universe is expanding faster than the model can account for, which would mean it's somewhat younger than we thought, and that we're missing something fundamental about the early universe, or about the force pushing it apart, or about the laws that tie those together. The difference between the two numbers isn't bookkeeping. It's the difference between a universe we understand and a universe we've been describing with the wrong equations. Which brings the suspicion around to that pushing force, the thing driving the whole expansion in the first place. We've been treating it as a fixed, unchanging constant. Nearly every calculation in cosmology leans on that assumption, and the newest, largest survey of the expanding universe has started to suggest the assumption might be wrong. What if the one thing we were most sure was constant has been changing all along? For most of the last century, the expectation about cosmic expansion was simple and, frankly, sensible. The universe is full of matter, and matter has gravity, and gravity pulls things together, so the expansion should be slowing down. Everything tugging on everything else, the cosmos gradually applying its own brakes, maybe slowing forever, maybe even reversing one day. That was the reasonable bet. Gravity only pulls, and pulling should win eventually. In the late 1990s, two teams set out to measure exactly how much the expansion was slowing, using distant stellar explosions as their markers. They expected to clock the deceleration. Instead, the distant explosions came back fainter than they should have been, and fainter meant farther, farther than a steadily slowing universe could account for. The expansion wasn't breaking, it was accelerating. Something was pushing space apart faster and faster, overpowering all the gravity of all the matter in the universe. Why fainter meant accelerating is the logic that made the result undeniable. The explosions those teams used are a special kind, stellar detonations that all blow up at very nearly the same true brightness, because they happen the same way each time. That sameness makes them rulers. If you know how bright the flash really is, then how dim it looks tells you how far away it is cleanly. The teams measured a batch of these explosions and found them dimmer than expected, which meant they were farther away than they should have been for how fast they were receding. The only way to put them that far out was if the expansion had sped up since their light was emitted, stretching the distance more than a steadily coasting universe would. Two independent teams, working separately, reached the same impossible-sounding conclusion at nearly the same time, which is a large part of why it was believed. The work was honored with a Nobel Prize, and it forced cosmology to swallow something nobody had ordered. For the expansion itself, the old image still works best. Draw dots on the surface of a deflated balloon, then inflate it. Every dot moves away from every other dot, not because the dots are crawling across the rubber, but because the rubber between them is stretching. There's no special dot at the center. From any dot's view, all the others recede, and the far ones recede fastest. Galaxies are the dots. Space is the rubber. And the discovery of the late 1990s was that the balloon isn't just inflating, it's inflating faster and faster, as if something were blowing harder over time. That was a real shock, and it forced a new ingredient into the theory. A pushing influence woven into space itself, working against gravity on the largest scales. We named it dark energy, which is mostly a label for our ignorance. The leading idea is that it's a property of empty space, that the vacuum itself carries a faint, relentless outward pressure. And as space expands and there's more vacuum, there's more push. In the standard model of cosmology, this dark energy is treated as a constant, a fixed property of space, the same density everywhere, the same yesterday and today and a billion years from now. That assumption of constancy is built into nearly every calculation we make about the universe's past and future. And it carries a prediction about the end of everything. If dark energy is constant, the acceleration never relents. Galaxies drift ever farther apart, faster and faster, until distant ones recede beyond the reach of light entirely. Stars burn through their fuel and wink out. New stars stop forming. Over unfathomable spans of time, every source of heat and light spreads so thin and so cold that the universe settles toward a uniform darkness, barely above absolute zero, a long, quiet, irreversible fade, the slow ending. The one most cosmologists have expected for decades. But that ending depends entirely on dark energy staying constant. And an instrument built specifically to test that assumption has started returning data that doesn't quite fit. The way you test it is by measuring the expansion not just now but across the depth of cosmic history, tracking how fast the universe was stretching at many different epochs, billions of years apart, to see whether the push has held steady or shifted. To do that, you need an enormous, three-dimensional map of the universe. Millions of galaxies and brilliant distant beacons, each one's position and distance pinned down, together forming a record of the expansion stretching back through most of the universe's life. A dedicated survey has been building exactly that map, capturing the light of thousands of galaxies at once, charting the expansion history across roughly 11 billion years. Inside that map is a kind of fossil ruler. In the early universe, before galaxies, pressure waves rippled through the hot primordial gas and then froze in place as the universe cooled, leaving a faint, preferred separation between clumps of matter, a characteristic distance baked into the distribution of galaxies. That distance acts as a measuring stick of known length. By watching how the apparent size of that stick changes at different cosmic epochs, you can read off how fast the universe was expanding at each one. It's one of the cleanest tools in cosmology, and the new survey applied it to more than 14 million galaxies and beacons. Last year and into this one, the results came in, and they carried a hint nobody ordered. Taken alone, the new map was roughly consistent with constant dark energy, but combined with the early universe radiation and other large surveys, the fit to a constant started to slip. The data leaned, gently but persistently, toward a dark energy that isn't fixed, one whose strength has changed over cosmic time, and the direction of the change is the surprising part. It suggests the push may have been stronger in the past and has weakened since. That dark energy's grip on the universe might be loosening, fading by something like 10% over the last several billion years. Think of a foot easing off an accelerator. The car is still speeding up. The universe is still expanding faster over time, but the pedal is being lifted, gently, so the acceleration isn't quite as fierce as it was a few billion years ago. The expansion still wins for now. The force driving it may be quietly running down. If that's real, it doesn't just adjust a parameter. It rewrites the ending. A dark energy that weakens could keep weakening. If it faded far enough, the acceleration could stall, and the expansion could level off. And if the push went further, if it crossed from a fading outward force into an inward one, then expansion could eventually stop and reverse. Instead of the long cold fade, everything that has been flying apart for billions of years would begin, slowly, to fall back together. The galaxies, the gas, the structure built over the whole history of the universe, drawn inward toward a single point, a reversed beginning, a collapse with enough intensity to undo everything that was ever built. Two endings could hardly be more opposite, and which one waits for the universe may hang on whether a number we assumed was fixed is actually drifting. Physics has a way of measuring how sure it is, based on how unlikely a result would be if it were just a fluke of random chance. On its own, the new survey's hint of changing dark energy sits at a confidence level that's interesting, but nowhere near decisive. The kind of result you note and watch, not the kind you build a new cosmos on. Stack it together with the other datasets and the confidence climbs, in some combinations reaching the range where physicists start to take a claim seriously as strong evidence. But strong evidence is not the same as proof, and the field has a specific, painful memory that keeps everyone honest about the difference. A little over a decade ago, an experiment in Italy measured a beam of those same ghostly neutrinos arriving a hair earlier than light itself should allow, a result that, taken at face value, would have shattered the speed limit of the universe. The confidence level was extraordinary, higher even than the gold standard physics usually demands before believing something new. It made headlines everywhere. And it was wrong. The cause turned out to be mundane and human. A faulty connection in a fiber optic cable and a timing error in a clock. Nothing had outrun light. An enormous statistical confidence had been built on top of a loose cable. That episode is why physicists, even staring at a result they'd love to be true, wait for the confidence to reach the highest bar and then keep checking the hardware. A number can be very sure and still be the product of a mistake nobody has found yet. So evolving dark energy is, right now, a tantalizing hint and not a verdict. More data is coming, the survey is still running, and other instruments are being built to measure the expansion across even larger volumes of space and to gather the enormous catalogs of stellar explosions needed to push the confidence to its limit. Within a few years, we may know whether the engine of the universe is truly running down, or whether the hint dissolves the way the faster-than-light neutrinos did. For now, the most we can fairly say is that the one quantity we were most confident was constant has started to look like it might not be, and that's enough to put the fate of everything back into question. Stop on the two endings, because they aren't equally weighted possibilities so much as a fork that depends entirely on the behavior of dark energy, and following the fork shows how much rides on a single uncertain number. Take the first road. Dark energy is constant, exactly as the standard model assumes. Then the future is already written, and it's a long, slow erasure. The expansion never stops accelerating. Galaxies that are now visible drift apart so far and so fast that their light can no longer cross the widening gap to reach us. And one by one they slip beyond the horizon of what can ever be seen, until a far future astronomer would look out and find the sky nearly empty, the other galaxies gone, only the local huddle of nearby ones left. Inside those, the stars burn through their fuel over trillions of years and go dark, one generation at a time, with fewer and fewer new stars forming because the gas to build them runs out. Eventually, the last stars cool. Whatever structures remain decay over spans of time that make the current age of the universe look like a single tick. Heat spreads so evenly and so thin that no energy can flow from anywhere to anywhere, because flow requires a difference, and every difference has been erased. The universe doesn't end in a bang. It ends in a sameness, a cold, dark, motionless equilibrium where nothing further can happen, sometimes called the long freeze. By most reckonings of constant dark energy, this is simply where everything is headed. To make that timescale even faintly graspable, set the star's era against the freeze. Stars have existed for something like the last 13 billion years. The era in which stars can still form and shine is expected to last, very roughly, on the order of trillions of years, and then the dark, starless stretch that follows isn't measured in trillions, but in numbers so much larger, they're written with exponents nobody can picture. If you compress the entire bright, star-filled age of the universe, past and future together, into the first single day of an immensely longer calendar, the rest of that calendar, the cold and empty part, would run on for a length of time so far past a day that the comparison stops meaning anything. The lit chapter is a sliver at the very front of an almost endless dark. Now, take the second road, the one the new hint about fading dark energy cracks open. Suppose dark energy isn't fixed. Suppose it's been weakening, and keeps weakening. If it merely fades and levels off, the acceleration could stall, and the expansion settle into a slower drift, a gentler version of the same long cooling. But if it weakens further still, past the point of merely fading, and the outward push turns into an inward pull, the story reverses entirely. Expansion slows, stops, and begins to run backward. The galaxies that spent billions of years flying apart start, imperceptibly at first, to fall back together. Over enormous spans, the gaps close. The structure that gravity and time assembled gets crushed back inward. Temperatures climb as everything compresses until the whole universe is racing toward a single point, a reversed beginning, a collapse intense enough to undo every galaxy and star and atom that was ever built. The mirror image of the explosive start, played as an implosive end. Two more opposite fates are hard to imagine. One is an endless thinning toward cold and silence. The other is a violent gathering back into a single furious point. And the thing standing between them, the thing that decides which future is real, is whether one quantity we long assumed was a fixed constant is actually drifting, and if so, how far it drifts. A property of empty space, measured across billions of years from the light of dying stars and the faint ruler frozen into the early universe, holds the entire ending in it. We do not yet know which way it tips. The newest data has only made the question live again. And that uncertainty about the far future folds back into a humbler unease about the present, because a model that can't yet tell us how everything ends is a model with something unfinished at its core right now. There's something we've been doing all night. We keep talking about dark energy as though naming it were the same as understanding it. It isn't. The name is a placeholder, a label stuck on a measured effect. The universe accelerates, whose cause is still unknown. And when physicists try to work out what it actually is, they run into a discrepancy so enormous it has a reputation as the single worst prediction in the history of science. The most natural candidate for dark energy is the energy of empty space itself. According to quantum theory, a vacuum is not truly empty. Even in perfectly empty space, fields are never perfectly still. Particles flicker in and out of existence, and that restless activity carries energy. Empty space, in other words, should have a built-in energy of its own, and that vacuum energy would push outward, which is exactly the kind of thing dark energy seems to be. So the natural move is to calculate how much energy the vacuum should contain and compare it to how much dark energy we actually observe. The two numbers do not nearly match. They miss by a margin so vast it borders on comedy. The amount of vacuum energy that quantum theory predicts is larger than the amount we observe by a factor with roughly 120 zeros after it. To get a feel for how hopeless that is, set aside cosmology entirely. A factor of 120 orders of magnitude is so far beyond ordinary error that no analogy in the physical world is big enough to hold it. It's not like being off by the size of a room versus a city, or even a planet versus a galaxy. It's a mismatch larger than the number of atoms in the entire observable universe, many times over. Our best theory of empty space, applied to the most natural explanation of dark energy, gives an answer that is wrong by more than anything has ever been wrong in physics. And yet vacuum energy is still the leading idea, because the effect it describes is real. We just can't explain why it comes out so absurdly small instead of catastrophically large. If the vacuum energy were actually as large as the naive calculation says, by the way, the universe would have torn itself apart so fast that no galaxy, no star, no atom could ever have formed. The fact that we exist at all means the real value is almost unimaginably smaller than the prediction, fine-tuned, somehow, to a degree that itself cries out for explanation. Something is holding the vacuum energy down to a whisper, or our understanding of the vacuum is missing something fundamental, and nobody knows which. So other ideas are on the table. Maybe dark energy isn't the static energy of the vacuum at all, but a field that fills space and can change over time, which would fit naturally with the new hints that it's weakening. Maybe it's a flaw in our understanding of gravity itself on the largest scales, so that there is no dark energy and the acceleration is really general relativity behaving in ways we haven't grasped at cosmic distances. Maybe it's some defect woven into the fabric of space left over from the early universe. Each of these is a serious proposal, and none has won, and they make different predictions about whether the push should be constant or changing, which is exactly why measuring whether dark energy evolves matters so much. The data isn't just refining a number. It's trying to decide between completely different pictures of what the largest component of the universe even is. The thing we understand worst, to the tune of the worst prediction in physics, is also the thing there is the most of. Dark energy is the majority of the universe, around 2/3 of everything, and it's the component our theories handle most embarrassingly. We are not slightly unsure about a minor ingredient. We are profoundly, measurably ignorant about the dominant feature of reality. And the strangest cracks aren't only in the deep future or the contents of empty space. Some of them are about right now, about motion we can measure today, because while the universe as a whole flies apart, our galaxy is also being pulled, hard, steadily, in a particular direction, towards something massive enough to overrule the expansion across hundreds of millions of light years. And when we look to see what's pulling us, the mass we find isn't enough to explain the pull. What is out there, hidden behind our own galaxy, heavy enough to drag the Milky Way across the universe? Everything moving apart is only half the story of how things move. The expansion stretches the distances between galaxies, yes, but gravity hasn't given up. Where matter is concentrated enough and close enough, gravity pulls galaxies together faster than the expansion can pry them apart. That's why galaxies aren't perfectly scattered. They fall into groups. Groups fall into clusters. Clusters into superclusters, all held by mutual gravity against the general drift. Locally, on the scale of neighbors, gravity still wins. The expansion only takes over across the truly vast gaps where matter is too thin and too far to hold anything together. Our galaxy is caught in this pull, and not gently. The whole Milky Way, with everything in it, is moving through space at something like 600 kilometers every second, not drifting with the expansion, but falling, drawn toward a particular patch of sky. Put that speed at human scale. A rifle bullet leaves the barrel at under 1 kilometer per second. Our entire galaxy, every star and planet and living thing in it, is sweeping through space hundreds of times faster than a bullet, and we feel nothing because there's no wind and no wall in space to feel it against. Something in the direction we're heading is massive enough to reach across the gap and pull our entire galaxy and many others steadily toward it. The region it's coming from picked up a fitting name decades ago: the Great Attractor. It sits somewhere between 150 and 250 million light-years away, and the estimates of its mass are staggering, on the order of 1,000 trillion times the mass of the Sun, enough to outweigh many thousands of galaxies. That's the scale of thing it takes to grab a galaxy from that distance and pull it in against the general expansion of the universe. For a long time, it was almost pure mystery, and for a frustrating reason. The direction we're being pulled lies straight through the disk of our own galaxy, through the densest crowd of stars and the thickest lanes of dust, the part of the sky where our view outward is most thoroughly blocked. We are being pulled towards something we can barely see because our own galaxy is standing in the way, like trying to identify a distant bonfire through a wall of fog with a streetlight glaring in your eyes. X-rays cut through that obscuring disk better than visible light, and as the instruments improved, astronomers managed to peer into the region and count what's there. They found a great crowd of galaxies, thousands of them, a true concentration of mass. And then the count came up short. The galaxies in the Great Attractor region, added up, did not contain enough mass to produce the pull we actually feel. The thing tugging on us was real and measurable, and the visible source of the tug wasn't big enough to do the tugging. The mass didn't add up. Looking deeper revealed why. The Great Attractor isn't really the destination. It's a way station. Far beyond it, around 650 million light-years away, sits something larger still. An immense concentration of galaxies packed densely together, many thousands of them, with a mass on the order of 10,000 trillion suns, 10 times the Great Attractor's already enormous heft. It pulls everything within roughly 1 billion light-years of it, including us, and including the Great Attractor itself, slowly toward it. We are falling toward a thing, which is falling toward a bigger thing, and the bigger thing is so massive and so distant that its full influence reaches across a span of the universe it's hard to even write down. And our address in all of this has a name. When astronomers trace the flows of galaxies in our region, which ones are falling toward which, they found that the Milky Way sits on the outskirts of an enormous connected basin of galaxies, all of them streaming toward that distant concentration along the same great currents. It contains something like 100,000 galaxies and stretches a few 100 million light-years across. We are not a free-floating island. We're one galaxy near the edge of a single vast watershed, sliding slowly downhill toward the densest point we can find. And then, looking in the opposite direction, the picture gets stranger. On the far side of the sky from that great mass lies a region that seems to be pushing rather than pulling, a zone the surrounding galaxies all stream away from, as though it were repelling them. It almost certainly isn't repelling anything. There's no known force that pushes matter away like that. What's far more likely is that it's a great emptiness, a region with very little mass, so that galaxies near it feel a stronger pull from the dense regions on the other side and drift toward those instead. The emptiness doesn't push. It simply fails to pull. And against the tug of everything else, failing to pull looks like a shove. Astronomers gave the region a name that captures the illusion. They call it a repeller, even while suspecting it repels nothing and is simply the absence around which everything else flows. A few researchers wonder whether some real unknown push could be at work there. But the simpler reading is that we are being herded as much by where the universe is empty as by where it is full. Our galaxy's motion through the universe seems to be set by both at once, pulled toward the densest crowd we can find, and pushed, in effect, from the emptiest void behind us. There's evidence that the Milky Way carries ripples in its structure, the kind of disturbance left behind when something massive passes through or collides with it. For a while, we couldn't identify the culprit because it, too, was hidden behind the glare and dust of our galactic disk. The likeliest candidate turned out to be a large but extremely diffuse galaxy, so spread out and so well hidden behind our own disk that despite its size it had gone unnoticed. Massive, real, and nearly invisible, recognized mainly by the marks its gravity left on us. Notice the pattern that keeps surfacing here: the Great Attractor's missing mass, the hidden galaxy behind our disk. The void that pulls by, not pulling, over and over. The things steering the largest motions in our corner of the universe are things we can't directly see, inferred only from the gravity they exert on the things we can. And this is the doorway into the largest version of that same problem, because the missing ordinary matter from earlier, the gas in the filaments, was never the whole story of the universe's hidden mass. It was only the part made of ordinary atoms. The far bigger reservoir of unseen gravity is made of something else entirely. Something that has never emitted a single photon, never absorbed one, never interacted with light in any way we can catch, and yet outweighs all the ordinary matter in the universe several times over. If the gravity holding galaxies and clusters and the whole cosmic web together comes mostly from something we cannot see and have never directly detected, then how confident can we really be about the scaffolding of everything? This particular discrepancy is almost a century old, and it began with a single galaxy cluster behaving wrongly. In the 1930s, an astronomer measuring how galaxies moved within a large cluster noticed they were traveling far too fast. The galaxies were whipping around at speeds that the combined gravity of all the cluster's visible matter could never produce. At those speeds, the cluster should have flung itself apart long ago, galaxies scattering into space like sparks off a wheel. Yet there it was, intact, bound together by a gravity far stronger than its visible contents could supply. The conclusion was uncomfortable but unavoidable. There had to be more mass present than anything that could be seen, some unseen substance holding the cluster together. It was given a name that meant, essentially, the dark matter. Then, in the 1970s, a different astronomer studying how stars orbit within individual spiral galaxies ran into the same wall from another angle. In a spinning galaxy, the stars far out at the edge should, by every expectation, orbit more slowly than the stars near the crowded center, the same way the outer planets of our solar system orbit far more slowly than the inner ones, because the pull weakens with distance from the central mass. But the outer stars of these galaxies weren't slowing down. They were circling just as fast as the inner ones, fast enough that they should have been flung off into space entirely. Something was holding them in, some mass spread far beyond the visible edge of the galaxy, reaching out past all the stars, gripping the outermost ones and keeping them from escaping. The same conclusion, arrived at independently, in a completely different kind of system. There is far more mass than meets the eye, and the visible galaxy is only the bright core of something much larger and unseen. What this dark matter actually is remains unknown, and that's not a small admission. We know how it behaves. It has mass, so it produces gravity and responds to gravity, and that's how we detect it, by its pull on visible things and by the way its gravity bends the light of more distant objects passing nearby. But it does not interact with light itself. It emits none, absorbs none, reflects none. You could be moving through a dense current of it right now and have no way to feel it. It passes through ordinary matter, and through itself, almost untouched. Every attempt to catch a single particle of it directly, in detectors built deep underground and shielded with great care, has so far come back empty. We have mapped its presence across the sky through its gravity, and we have never once held a piece of it. That last fact deserves an honest objection, the kind a sharp skeptic raises immediately. If you've never detected this stuff directly, and you're only inferring it from gravity behaving strangely, isn't it just as likely that you've got gravity wrong? Maybe there's no invisible substance at all. Maybe the law of gravity, which we tested in the solar system and assumed holds everywhere, simply behaves differently at the vast, faint scales of a galaxy's edge, and what looks like missing mass is really just a force we've misdescribed. It's a serious idea, not a crank one, and some physicists have spent careers developing versions of it. Tweak the rule of gravity in the right way, and you can reproduce the fast-spinning galaxy edges without inventing any new matter. The reason most cosmologists don't think modified gravity is the whole answer comes down to cases where the unseen mass and the visible mass come apart in space. When two galaxy clusters collide and pass through each other, the ordinary gas in them slams together and slows down, while the unseen mass appears to sail straight on through, ending up separated from the visible matter. We can map where the unseen mass is by watching how its gravity bends the light of more distant galaxies behind it, a separate, direct consequence of mass that doesn't depend on any spinning. And in those collisions, the bending shows the gravity sitting where the visible gas is not. That's hard to explain by rewriting the law of gravity, because there's no visible matter in those spots for a modified law to act on. But it's exactly what you'd expect if there's a real substance there, invisible, that passed through the wreck untouched. The debate isn't fully closed, and that openness itself is telling. But the weight of evidence leans towards something being there, not toward our equations being wrong, which only deepens the mystery, because something being there means a substance we've never identified makes up most of the matter in existence. And there is a great deal of it. When the budget of the universe is tallied, ordinary matter, everything made of atoms, every star and planet and cloud of gas, the missing filaments included, comes to only about 5% of the total. Dark matter accounts for several times more, somewhere around a quarter of everything. The rest, the largest share by far, is the dark energy from earlier. Set those numbers side by side and the meaning is stark. The matter you can see, the matter telescopes have studied for centuries, the matter that makes up every object anyone has ever pointed at, is a thin, bright trim on a universe overwhelmingly made of two things we cannot see and do not understand. To put the proportion at human scale, if the whole contents of the universe were a stack of 20 coins, 19 of them would be made of substances no one has ever directly detected, and the single remaining coin would be everything we have ever observed. This is also, finally, what the cosmic web is mostly made of. The skeleton from earlier, the filaments, the scaffolding that ordinary gas and galaxies are strung along, is thought to be built primarily of dark matter. The faint, over-dense patches in the early universe that gravity grew into threads were dominated by it, because there's so much more of it to do the gathering. The bright galaxies and the hot filament gas are the visible residue clinging to a far larger invisible structure. We've been admiring the light strung on a web whose actual strands give off no light at all. When we map the web by its galaxies, we're tracing the dark scaffolding indirectly, the way you'd infer the shape of a darkened trellis from the pattern of berries hanging on it. So stand back and look at what the structure of the universe has turned out to be, piece by piece. The matter you're made of shouldn't have survived the beginning, and we can't say why it did. 40% of even the ordinary matter went missing for decades, and we've only just begun to find it. The rate the universe expands gives two different answers that won't reconcile. The force driving that expansion, assumed constant, may be fading. The pull steering our galaxy comes partly from mass we can't locate, and partly from a void that pulls by being empty. And the gravity holding the entire web together comes mostly from a substance that has never touched light and has never been caught. Every layer of the structure, examined closely, has something in it that doesn't fit. Faced with a pile of anomalies like that, you have two broad choices. You can suppose each one has its own separate fix. Patch the matter problem here, the expansion problem there, the dark energy problem somewhere else. Or you can wonder whether something simple and fundamental is missing from the whole picture. A single, overlooked feature that would shift several of these problems at once. And recently, a few researchers floated a candidate for exactly that kind of fix, an idea so basic it sounds almost naive, and which, surprisingly, doesn't break any known physics. What if the entire universe is slowly turning? Almost everything in the cosmos rotates. The Earth turns on its axis. The Moon circles the Earth circles the Sun circles the center of the galaxy, dragging the whole solar system along an orbit that takes hundreds of millions of years to complete. The galaxy itself spins. Rotation is so universal at every scale we can observe that there's something almost odd about the one assumption built into our cosmology, that the universe as a whole, the entire thing, does not turn at all. Standard cosmology assumes a cosmos that expands but never rotates, perfectly still in that one respect, uniquely so among all the things inside it. In a paper published early last year, a small group of researchers asked what would happen if you relaxed that assumption, if you let the universe rotate, just barely. Not the galaxies within it spinning, which they already do, but the whole fabric of the cosmos turning very slowly as one. And the rotation they considered is so gentle, it almost doesn't deserve the word. In their model, the universe would complete a single turn roughly once every 500 billion years. The idea of a rotating universe isn't new. Decades ago, working through the equations of general relativity, the logician Kurt Gödel found that those equations permit a rotating universe as a valid solution. A cosmos that spins is not forbidden by the laws of gravity. It's one of the shapes the laws allow. For most of the time since, that solution was treated as a mathematical curiosity, because our universe showed no clear signs of spinning, and the simplest assumption was that it doesn't. What the recent work did was revive the possibility with a specific, gentle rate and ask whether it could do useful work, whether a barely turning cosmos might quietly fix a problem the non-turning version can't. 500 billion years is so far beyond human reference that it needs anchoring, so set it against the age of the universe itself. The cosmos is a little under 14 billion years old. A single full rotation, in this model, takes 500 billion years, which means that in the entire history of the universe so far, from the first instant to right now, it would have turned through less than 3% of one rotation. Not 3 rotations, 3% of one. A motion so slow that across all of cosmic time, it hasn't yet come close to a single full turn. Slow enough that nothing we've measured would have plainly revealed it. There's no cosmic carousel to feel, no blur at the edge of the sky. From inside, a rotation that languid would be almost perfectly invisible. And yet, the researchers found almost invisible is not the same as without consequence. When they put that whisper of rotation into their model, something unexpected happened to the expansion. The math began to predict an early universe expanding at a lower rate and a present-day universe expanding at a higher rate, which is precisely the shape of the disagreement that's been tormenting cosmology. The two stubborn values of the expansion rate, the low one from the early universe and the high one from the nearby universe, both fell out of a single model that differed from the standard one only by adding a slow turn. The gap that wouldn't close under the usual assumptions appeared, in their preliminary calculation, to close when the universe was allowed to rotate. It would be easy to oversell that, and the researchers themselves were careful not to. This is an early result. A first calculation focused narrowly on the expansion rate problem. It is not a finished theory of the cosmos, and it has not been checked against the full range of other observations a complete model has to satisfy. The structure of the cosmic web, the pattern in the early universe radiation, the motions of galaxies on every scale. The next step is exactly that harder work, building the rotation into fuller models and testing whether it survives contact with everything else we've measured, or whether it fixes one problem while quietly breaking others. Plenty of elegant ideas die at that stage. This one might. But two things about it hold up regardless of whether it survives. The first is that it doesn't require tearing down physics. Some proposed solutions to the expansion crisis demand radical surgery, decaying dark matter, a modification to gravity itself, a rewrite of the rules on the largest scales. A slow, universal rotation asks for none of that. It violates no known law. It simply removes an assumption we had quietly baked in, the assumption that the universe doesn't turn, and asks whether the data prefers a cosmos with a faint spin. Even if it turns out to be wrong, it would still leave us, at minimum, with a rotating variant of our standard model, one where familiar cosmic quantities shift to make room for the turn. The second thing is the deeper one, and it reaches past this single idea. The rotation hypothesis works, to whatever extent it works, by questioning an assumption that almost no one had thought to question, because it had never seemed like an assumption at all. That the universe doesn't rotate wasn't a measured fact. It was a default, a simplification, something written into the equations because it made them cleaner and because there'd been no clear reason to doubt it. And that raises a quietly disturbing question about everything else in the model. How many other defaults are sitting in our cosmology like that one? Not measured, not proven, just assumed because they're simpler and no one has had reason to look. The constancy of dark energy was one such assumption, and the newest data is straining it. The non-rotation of the universe was another. Each of these had felt less like a claim and more like a part of the furniture, until someone moved it and the room changed. One of the researchers reached for an idea from an ancient Greek philosopher to describe it, the old notion that everything flows, everything moves, that nothing in the cosmos truly holds still. It's a fitting frame, and not only for the rotation. The longer you look at the structure of the universe, the more the solid-seeming pieces of our understanding turn out to be in motion themselves. The expansion rate that won't settle, the dark energy that may be drifting, the very stillness of the cosmos now in question. The structure we're trying to describe keeps moving, and so does our description of it. Which leaves a question that isn't about galaxies or dark matter or expansion at all. It's about us, about the instruments doing the looking, and the minds reading the results, and whether the trouble we keep running into is entirely out there in the cosmos, or partly in here, in the way we're built to see it. We see the universe through human eyes, with human senses, and we make sense of it with human minds carrying biases we didn't choose and mostly can't feel. That sounds like a soft observation. It isn't. It runs straight through everything we've covered, and it repays a closer look, because the way we're built to perceive shapes what we even count as strange. Start with the word that's been doing quiet work all night: strange. The universe's structure doesn't make sense, but sense to whom? Every time we've said something shouldn't exist or shouldn't behave this way, the standard we were measuring against was an expectation, and the expectations came from us. Matter and antimatter should have annihilated completely. That's an expectation built from a symmetry we find natural. The expansion rate should be a single number, natural to us, because we expect a quantity to have one value. The universe shouldn't rotate, a simplification we found convenient. Dark energy should be constant. The simplest option, and we tend to assume the simplest option is the true one until forced off it. At every turn, doesn't make sense has really meant doesn't match what a human mind expected. The universe is under no obligation to meet that standard, and the repeated mismatch may be telling us as much about the shape of human expectation as about the shape of the cosmos. We can know a great deal, and we've proven it. We put the matter imbalance at 1 part in a billion. We compared a proton to an antiproton to 16 parts in a trillion. We mapped a filament 23 million light-years long that the models predicted in advance. That is not the record of a species that knows nothing. It's the record of a species that knows enough to measure precisely where its understanding fails. The point isn't that knowledge is impossible. The point is that our intuitions about what's natural and what's strange are tools that evolved for a world of medium-sized objects moving at ordinary speeds, and there's no reason those tools should carry over cleanly to the scale of the whole cosmos. Light travels fast, but not infinitely fast, and the universe has only existed for a finite time. That means there is a maximum distance from which light could have reached us by now. A horizon. beyond which sit regions whose light simply hasn't had time to arrive yet. Everything we can observe, every galaxy and filament and the oldest light itself, lies inside that horizon. What's past it is not hidden by dust or distance in a way we could photograph if we tried harder. It's hidden by the speed of light and the age of the universe together, and the expansion is steadily carrying more of it permanently out of reach. So when we talk about the structure of the universe, we are always talking about the structure of the part we can see, a finite bubble centered, inevitably, on ourselves, not because we're special, but because every observer sits at the center of their own horizon. Whether the patterns we've found hold beyond it, whether the imbalance and the expansion and the web continue the same way out there or give way to something else entirely, is a question that may be not just unanswered but unanswerable, sealed off by physics rather than by ignorance. Some of what doesn't make sense might only fail to make sense because we can see just a piece of it. We're too early. We're too early in our history, too early in our understanding, to be asking these questions and expecting answers. And there's something true in it and something incomplete. What's true is that we are clearly early. Every one of the deepest questions tonight is open, and several of them have been open for the better part of a century, and the instruments capable of resolving them are only now being built or still being imagined. What's incomplete is the implied conclusion that being early means we should wait, or that the asking is premature. The asking is how earliness ends. Every precise measurement that doesn't fit, every anomaly sharpened rather than dissolved, is the process of a young understanding growing up. We are early. Early is not the same as wrong to be looking. When the structure refuses to make sense, it's tempting to conclude that it was made not to, that the fine balance which let matter survive, the precise values that let stars and galaxies and chemistry and life exist, point to something intended, something fine-tuned on purpose. It's an old and serious impulse, and it shows up wherever the numbers seem too precise to be accidental. The honest scientific position isn't to mock that impulse or to endorse it. It's to notice that we are very bad judges of how surprised we should be by our own existence, because we could only ever find ourselves in a universe that permitted us to be here to do the finding. A universe that annihilated itself would have no one inside it, marveling at how unlikely survival was. The marveling is only ever done by the survivors, in the one kind of universe where survivors are possible. That doesn't settle the deeper question of why the balance tipped the way it did. That question is wide open, and it's the one the antimatter factories are built to chase. It only cautions against reading too much certainty, in either direction, off the bare fact that we're here to ask. Hold all of it together, the limits of our senses, the biases in our intuitions, the youth of the whole enterprise, the pull to find intention in the gaps, and a particular kind of humility comes into focus. Not the humility that stops asking, the humility that keeps asking while holding its own answers loosely, knowing they'll be revised. The people closest to this data are comfortable saying the model might be broken, comfortable floating a rotating universe, comfortable admitting that the substance making up most of the cosmos has never been caught and the imbalance that built everything has never been explained. That comfort with not yet knowing isn't weakness in the science. It's the strongest part of it. A field that couldn't say, "We don't know," would have stopped finding things out long ago. So what do you do with a universe whose structure, examined without flinching, is a stack of open questions resting on a foundation that shouldn't be there? You could find that bleak, proof that we're small and lost and out of our depth. But there's another way to hold it, and it doesn't require pretending we know more than we do. Every one of these mysteries is something a person noticed. Someone measured a cluster moving too fast and refused to look away. Someone counted the ordinary matter and admitted that nearly half was missing rather than fudging the books. Someone let the universe rotate in an equation just to see. The not knowing isn't the absence of understanding. It's the live edge of it, the place where the work is actually happening. And the strangest part of the whole picture is the one easiest to forget while staring out at filaments and superclusters and the great hidden masses pulling the galaxy along. All of this, the surplus that survived annihilation, the matter that built the web, the expansion, the unseen majority, is not only out there, it is also, right now, the thing doing the looking. When you go looking for the universe, where exactly are you standing? The matter you're made of is the surplus, the 1 in a billion that didn't annihilate. There is no separate special material that life is built from. The carbon in your cells, the oxygen in every breath, the iron in your blood, the calcium holding you upright. Every atom of it is a leftover from that first cancellation, a particle that happened to have no partner to vanish with. You are not watching the survival of matter from the outside. You are made of the part that survived. The question of why there's something instead of nothing isn't an abstract one for you. You are a piece of the something, assembled from the rounding error of the universe. And those atoms were not made at the beginning. The lightest elements came from the early universe, but the carbon and oxygen and iron, the heavier atoms your body depends on, were forged later, inside stars, under pressures and temperatures nothing on Earth approaches, and scattered out when those stars died. They drifted through the thin gas of the galaxy, gathered into the cloud that became the sun and its planets, and ended up here, arranged into something that could notice them. The same web of structure we traced across the sky, the gathering of matter under gravity, the collapse of clouds into bright, dense knots, is the process that built the raw material of you. You are local cosmic structure. The web didn't just produce galaxies. On at least one strand, it produced something that could look back at the web. The expansion is in you too, in a sense that needs to stay precise so it doesn't become a slogan. Space itself is stretching everywhere, but on the small scale of a body, or a planet, or a galaxy, gravity and the bonds between atoms hold everything together far more strongly than the expansion can pull it apart. You are not being stretched. The expansion loses, easily, at the scale of a human being. But the same force that's negligible across your body is the dominant fact of the universe across the gulfs between galaxies. The same physics, the same equations, producing nothing you'll ever feel here, and the entire fate of the cosmos out there. The difference between the two isn't the law, it's only the scale. Even the not knowing is in here, not just out there. The dark matter we trace through the galaxy by its gravity is, as best we can tell, streaming through you continuously, a current of unseen mass passing through the room and through your body without a whisper, billions of those ghostly neutrinos pouring through you every second alongside it, almost none of them ever touching a single atom of you. The mysteries aren't all at the far end of a telescope. Some of them are passing through your chest as you breathe, undetected, because you are made of the kind of matter that barely interacts with them. The universe's invisibility isn't only a fact about deep space, it's a fact about the present contents of the room you're in. So gather the whole arc back to this point. The matter that shouldn't have survived is your body. The structure that shouldn't quite add up is the lineage that built your atoms. The expansion that will decide the fate of everything is the same physics that, at your scale, does nothing at all. The invisible majority of the cosmos is drifting through you right now. Every layer of the strange, unfinished, doesn't make sense structure of the universe is not a distant spectacle. It converges, physically, on the small, warm space where you happen to be. A temporary arrangement of surplus matter, briefly organized into something that can ask where it came from. We don't know why the matter you're made of is here. We don't know what most of the universe is made of. We don't know why its expansion gives two answers, or whether its driving force is fading, or whether the whole thing is faintly turning. The structure of the universe, examined as plainly as we can examine it, does not yet make sense, and you are a part of that structure, made of its unexplained surplus, holding its unanswered questions inside a body built from the very matter the questions are about. The universe made something out of almost nothing, for reasons it has not surrendered. And then it made a small portion of that, something capable of noticing the whole arrangement and asking why. If the matter you're made of is the part that wasn't supposed to last, What is it doing, lying here in the dark, wondering about its own beginning? Thank you for staying all the way to the end, for giving your quiet hours to questions that don't hand back any answers, when the night had easier things to offer. That isn't a small thing, and I'm grateful for it. None of this got resolved, and you don't have to carry the not knowing with you. The questions have waited longer than anyone alive, and they'll still be here in the morning. You can set them down. So let the room go quiet, and let yourself be the surplus matter at rest for a while. Good night. Sleep well.